This is a Math 3 lesson summary video for the lesson titled Box It Up. This is a develop understanding task. The purpose of this task is for students to apply geometric concepts and modeling situations and use the volume formula for a rectangular prism to solve problems. Students will model the relationship between the height and volume of a rectangular prism, and then use the model to maximize the volume of the prism. Students will build on their previous work in this course involving cubic functions and their work in previous courses involving volume. In this lesson, students are asked to maximize the volume of a box. The box is made from a rectangular piece of cardboard. The square corners of the cardboard are cut out and the sides are folded up to make the box. This problem asks students to maximize the volume by determining the best size of square to cut out of each corner. After finding the size of the square, the students then find the dimensions of a box that has the largest possible volume. Let's start by looking close at this box and its possible dimensions. If the corners of the box are 3 units long, then the height of the box is also 3 units long. That means that the width will be 22 minus 2 times 3, so 16 units, and the length is 28 minus 2 times 3, which is 22 units. The box is a rectangular prism, so the volume is found by multiplying the length times width times height. This produces a volume of 1056 cubic units. But the question is this the largest possible volume? Is there another box height that could produce a larger volume? We're interested in finding the height of the box that maximizes volume, so we need to define our variable x as the height of the box, which is the same as the size of the side length of the corner square. The width of the box can be represented as 22 minus 2 x's, and the length as 28 minus 2 x's. This is still a rectangular prism, so to model the volume of the box when the height is x units long, the volume is still found by multiplying length times width times height. This gives us a function formula. Next, let's look at the graph in the table of this function. By using Desmos and adjusting the window, we can get a better look at the function. The practical domain, which represents the possible values of x, or in other words, the possible heights of the box, are values between 0 and 11. If x was less than 0 or greater than 11, then the box would not be able to be physically constructed. If the height of the box was 0, then the box would be a flat piece of cardboard. And if the height was 11, then the box wouldn't have a width. The practical range, or in other words, the possible volumes of the box, are values between 0 and 1120.31 cubic centimeters. By using the table, we can see that when x is equal to 4, the volume is 1120 cubic centimeters. By using Desmos's maximum finding feature on the graph, we can click to see that when x equals 4.078, the volume is a little larger at 1120.31 cubic centimeters. This maximum value is what we're looking for. After looking at the representations of the function and finding the maximum point, we can use this to find the other dimensions of the box. The height of the box, x, is equal to 4.078 centimeters. The width of the box was 22 minus 2x. By substituting the values into the expression, we can find that the width that will produce the maximum volume is 13.844 centimeters. And then using substitution again, we can find the length that will produce a box with the largest volume would be 19.844 centimeters. This means that we now have all 3 dimensions of the box that will have the largest volume. If we multiply these dimensions together then we would get the maximum volume that we already have found of 1,120.31 cubic centimeters. In this problem, after we determined what we needed to find, which was the dimensions of the box that maximized the volume, we identified the shape being modeled as a rectangular prism. Then we used a familiar formula for the volume of a rectangular prism to create a function. To create the function, we first created expressions to represent each dimension or piece of the formula, and then we built the function by substituting in expressions of the dimensions. Since volume has 3 dimensions, functions that model volume are cubic. We used what we learned about cubic functions in the previous unit to find the maximum and solve the problem. Alright, that's it for this video. Thank you for watching.